Because we are talking about the equation motion and IBP. So, when you define the character for the space-time symmetries, just looking to the loading character is not sufficient. So, because if it is a loading character, then what we will do? We have a SL2C or SO4 constant that we will realize in terms of SC2 or SC2, and then we write down the characters, right? But something more than that we want to do. We want to improvise those character configurations in such a way that automatically take care of the equation of motion and IBP constants. That means once we rephrase and review those character configuration and end up having some kind of character for non-zero spin particles and also scalar particles, you can guarantee that once we plug in the precision, so this will be the precision corresponding to the space-time symmetry. So if you recall, for the internal symmetry, we have a precision corresponding characters of the internal symmetries, right, which are basically compact groups, and there is corresponding hard measure for that. And the purpose of the hard measure was basically to project out all the invariants under the internal symmetries, right? And this will be the separate construction with respect to the space-time symmetry. So now when we ask for the invariant operators, which are invariant under this internal and space-time symmetry, we will just do them. And because internal symmetry and space-time symmetry, they don't talk to each other, so we can just independently construct them and let it do them. Right? So that will be a hard measure of the product of the hard measure under the internal symmetry and the space-time symmetry. But space-time symmetry is special because unlike the internal symmetry, here we have additional constant apart from even after being an invariant. Even after being an invariant, there are additional constants, and those constants come in terms of equation of motion and integration of parts. Okay, and both the things are actually there because of derivative operators. If you switch off derivative, okay, then you will not feel this kind of constants because these constants are not being generated by them, and that's why we need to have primary focus on that, and that's your time to learn how to write down the character. Now, why we need to upgrade our logic to control group? Because there is no room to accommodate derivative inside the manual symmetries. Because that is already occupied for your spin states, so you need something as a transition, which is basically here the degradation. And to accommodate that, if you remember that Q variable that we are actually writing originated from the degradation theorem, and the eigenvalues are basically the dimensions. And we have seen that basically that the value that because we are working in unitary representations, so for the field theory, those delta or the control dimensions are basically nothing but my first dimension of the particles or the field package.
If you just want to include the translations, why don't we use ISO? ISO 311.
Those are already inside that when you write them in terms of SC2, SC2R. But that doesn't give you the scaling dimension.
That will be component on one.
Yes.
But if I do want to do the translations, that will be
Translation is the moment of translation we are talking about, right? But that doesn't give you a decimal numeric operator for the scaling dimension. So you need a scaling dimension for that thing. If you do not have a scaling dimension, how do you parameterize your theory? Right? Okay. And also, when the action of a derivative, when you do, the scaling dimension of the operators are changing. Where do you get that information? It's like a team, but actually more dilatation compared to the transition. Okay. So that's what we're trying to learn that. And then then that's why from Y character representation, what we did for the internal symmetry, we have to construct the Verma character. Because Verma character is something very interesting object which allows us to do this kind of construction. And that is the reason you will see we deviate from the Y character calculation to the Verma character calculation. Okay. And what was the Verma character? We are writing in terms of SU2L, SU2R, and there is SO2, which is integration. So SO2 character is equivalent to your U1 character. If you cross coordinate your Q, for the equivalent is Q, we got the charges. And for that, charges are basically the eigenvalues of the generator. And that eigenvalues is nothing but the scaling dimensions. That's why Q is equal delta comes into the generator. And then SU2L, SU2R is basically your chi half and chi half. And because they are independent, so we have to introduce two different cross variables x and y. We got right. But also we argue that if you write down just q to the power delta chi half x, chi half y, if you got that we write down the as q to the power delta, more than we write down. Right? So this is the character of SU2L per SU2R plus of SO2R T1. But we are writing the character for SO4 and that's where these objects are. So once you do the P, which you realize as the momentum generating function, okay, the whole thing is the series for the Verma character. So this is the Verma character for a long representation. Now, when you write down these characters, as I mentioned, these are long representations. So, what is the meaning of long representations? That if those representations suffer from any kind of constraints, they are not taken care of. This is just, like for example, when you write down the character and the internal symmetry, you are writing the phi, depending on the charges. How does it transform under the symmetry? Write down the character. That's basically the long representation you can consider that. But now on top of that, any question? Now on top of that, what is interested in that if those objects which are basically now like fields, because at the end of the day, we have to upgrade them as a quantum field, like the spurions which are calling them. And in the quantum field, when we are writing, those are basically dynamical variables for us. If we are constructing the operators in terms of some dynamical variables, then they will have some equation motion. As I told you, the free equation motion is independent of the interaction, just the triangle term. And all the interactions will be generated from the basic space. Okay. So, we can track down the dynamics from the free equation motion. And equation motion is like a constant. Right? And the classical mechanics we have learned that there is a 2D object and if you just roll a ball, okay, there's some kind of dynamics that tells you along the which trajectory you should go. It reduces the arbitrariness in its movement. That's what it does. Because what is the equation motion? It's like a differential equation. And once you have certain kind of boundary conditions, that gives you trajectory. It is the only trajectory along which that objects pass through. Similar that, so in all language, the equation is like a constant. So when I'm writing a long representations, it tells you all kinds of arbitrariness are involved there. But we don't allow them to do that. We don't allow phi to be evolved. Okay, arbitrary. We want to evolve that phi in a particular way. And that particular way is driven by the equation motion. When you solve that, you know how, because you don't expect the phi to be moved like a fermion, because it's scalar. You don't expect fermion to be moved like a flying bottom field, because then your whole field will be construction will be formed. That means we have to not only identify those objects, but also if their dynamics are known to us, that information should be injected while doing the calculation. And how we do this in our construction? Actually, write down the most generic character which we call the long representations, and then we impose the constant. And impose the constant means basically we remove those non-state. For example, the scalar, as in the d2 phi equal to 0. So from the scalar character, we remove the d2 phi part. For the fermion, we know the fermion character we write down in that j1 and j2 equal to half. Right? So if you are in the left chiral, j1 equal to half, j2 equal to 0. Now if you are working in the right chiral, j1 equal to 0, j2 equal to half. Right? But then you remove the equation of motion, which is basically d slash psi equal to 0. And as you know that d slash psi, if you write down the state that you are removing is basically in the right chiral. And that's why we have written down last time that from the left chiral primary or left chiral long representations, we remove the right chiral state. So that's how the equation would be, and vice versa. But we have to now be careful while writing that what we are removing, is there any kind of further constant on that? For example, if I have d2 phi equal to 0, but there is no additional constant on that. The d2 phi equal to 0 is an absolute statement. Similarly, d slash psi equal to 0, that's an absolute statement because there is nothing we are removing. But is that the similar thing we can say about the field tensor? Because let's say you have the field tensor you are writing, right? F mu. Now, you can write down the long representation of that mu. So how do you write down that thing? So if you talk about the left chiral left mu, then it will be j1 equal to 1, j2 equal to 0, or vice versa. But then, what I am doing? The divergence of that, because that is the equation of motion for this thing. What is that? That is current. D mu F mu equal to j mu, right? But now you see, D mu, if there is a constant, the current is constant, then this j mu is not itself a sort of equation. You have to now impose another further constant because now d mu acting j mu is equal to 0. Right? So that means if you are dealing with the point of view theory, and if these are the symmetries of your theory, then of course those currents are constant, because that's why the Noether's theorem. Okay? So we have to give the provision that the constant current character has to be taken care of suitably when you write down the character for the FU. That's why the FU are the specific. And that is not only for the FU, but once you go for higher form object, you will feel that repeatedly happening. So what was trivial for us for the scalar and fermion case, okay, that is slightly different for the field case. And that we do how to deal with that. But in the schematic picture clear to all of you how we are proceeding, because that's more important, because algebra will follow. But the arguments and all those things should be properly understood first. Right? So then, what we learn, is we write down basically these words in our definition as a d log by and what we are mathematically we are calling the null state is basically the state generated by the equation of motion. And that's why removal of the null state is equivalent to imposing the constant of the equation of motion. Okay. So then, for the scalar, we write down the character I have go step by step because it's already we have done this one, right? Because Q's, so why you remove the d cube part? Because d square phi has the marginal simplicity and d square phi for one character is 2. That's why you are writing this. Now, fermion case, we write here chi psi as d by 2 x way around. Just the exchange of x and y. Okay, that's the point. Right. So now about the field tensor. Okay. And as you can see that we are not writing anything in terms of the gauge fields, because gauge fields are not the degree of freedom for us in this construction. So we will talk about only about them, which are basically degree of freedom for us, and in this construction we are calling them prime. So what we have here, FL is basically F alpha beta 1 0 and F r equals F alpha dot beta dot equals. Right? So that's how you realize in terms of SC2 to SC2R. And SC2R contains the dotted index. So basically, if you think about the epsilon alpha beta, which is the metric in the SC2 space, which is equivalent to your I sigma, and that's how basically you change. If you remember what was already at the beginning said that okay, if I have SC2, what is how to write down the conjugate representation of two-dimensional equation? It's not 2 star, it's a 2 bar. What is the definition of 2 bar? Because we have to write down the conjugate representation in such a way that it has a proper SC2 transformation. 2 bar, 2 star doesn't have SC2 transformation. 2 bar is basically I sigma to 2 star. Okay, so that's why if you have let's say 5 1 5 2, then 5 2 star minus 5 1 star. That is the actually transformation. So that's the singular representation. That's why they are saying equivalent. And that is why if you have done that in this course, you remember in the standpoint we have only one star, H. Right? But using that H, you cannot give the mass to upper and lower final thing. So you have to convert and H into I sigma to H theta. Right? And so without changing the degree of freedom of the system, I can play this game within that system. Okay. So now this I sigma is basically epsilon metric in the SC2. So basically, what is the part of the metric? Like making a coherent to contrametric kind of, right? So alpha beta, epsilon alpha beta is the metric in the SC2 L space. Epsilon alpha dot beta dot is the metric in the SC2 R space. And that's what here I'm using the alpha dot beta and alpha beta. And you can see there are two orthogonal spaces. So you cannot just contact alpha and alpha dot. You need two different metric to raise and bar. Okay. So now, if I write down there, so basically I write down I1 x. This is my long representation from them. This is my long representation. Right? Do you agree? I am not writing the chi. I could write down the chi 0 1. But what is your chi 0 1? 1. You singlet. So IBP. That's why I'm not writing. But in principle, if you write down, that will be I 0 y, which is I. There will be I 0 x, and that will be I. Okay. So then, what I'm doing, if I have half of state, and then I'm doing this. What is the equivalent description you get from here? So you create G bar to half. And half of state. Right? So, what is the physical description of this tensor product? It is actually saying that you have a bicycle. What is a bicycle? D acting on the equilibrium. Okay? And you generate this state. But more importantly, this state. What is this state? This is a vector bicycle. Okay? And this is exactly your J. So this has a physical description what you are writing as a n beta alpha dot e alpha dot. Why? Because see, D is bicycle, so you have one alpha dot. A is basically left parallel alpha contracted. So now, what the object I am creating is 1 beta and alpha. That means it will be also vector. Vectors will have a mixed alpha and alpha dot pieces. Okay. So this in the field theory language, what you will write down as a find out this part. If you don't understand, please let me know. Okay, everyone? Okay. So now, that means basically from this long representation, I have to remove this character. Okay. So let's remove the character. What is the character? U. And then I R. Yes. I R. 1. Because the level 2 operator, level 1 operator, because we start with primary, so I add 1 derivative, so I increase basically my conformation by 1 unit, that's a q square become q cube. Okay, and then it's a pi square, so you have. So I remove that equation. But now, this genuine is something which is actually conserved. So that means this genuine is not an arbitrary genuine. Right? So if I take a derivative on the genuine, what is the definition of conserved part? dmu genuine equal to 0. Right? Now dmu genuine, what kind of object this is? Scalar? Right? So that means when I am writing down the genuine character, that genuine character from the genuine character, I have to remove that scalar because that's a constant. Right? So that means we have now for that equal to 0 is the conserved time, and now which basically in the terms of d beta alpha n beta alpha equal to 0. And now you can see everything basically contracted, alpha dot and beta, all the units are contracted. And if all the units are contracted, that becomes a scalar. So that means we have to remove that from the genuine character. So effectively when we write down, we write down e to the power 4, then I0 x, I0 y.
What do you get here? Equals to 0. That will be the same statement.
Sorry?
Like dmu is basically dmu FPD equals to 0.
Yeah.
So can we not just take the character of this whole thing like dmu FPD, then
Yeah.
it may be for that just write it down on the.
Yeah, but how would I tell the character? How would I tell the dmu acting on the FPD? Basically, if I have n number of dmu acting on some tensor, let's say rank m tensor, how would I tell the character for that? No. That means you have not learned what is the character. So first, character is not just what is the final product. The intermediate steps are also important. If I am writing, let's say, d mu1 to mu p acting on some object, let's say mu1 to mu r, okay, and value r is greater than equal to p, let's say. Okay. Then I can take this character. What coefficient should write down the character? That's what we are asking, right? We are asking, okay, why not I am writing the character for dmu of the dmu equal to 0? Okay? So, if without going through this, if I write down this thing, can I write down the character? Or more generally, if I have this, what prohibits me to write down the character? You can answer only when you understand how we are writing the character. Why that each and every step are important? The reason is basically, we have to understand that when you start with the primary, and in this particular this one is the primary, this one is the primary, okay? And then every action of B, what is my outcome? What is the property of that? It's not guaranteed that each and every step you get a constant quantity. Right. Also, it is not guaranteed you will always get a symmetric object. Very simple. Just you are getting tan two tensor, you will add one derivative of the single vector. But you have higher form object. You don't guarantee all of these are symmetric to the action of derivatives. So some objects will be identically zero because the antisymmetric property. Some will be zero for the constant. Right? Some of them may not be zero and give you something defined. So we need to know what is that something defined acting on those objects. Right? So that's why the argument would be you start with primary, you act a derivative. What is your outcome? Look into that. And what you are getting after one action of derivative is that quantity symmetry, anti-symmetry, or how does it transform, if it comes out, all the things you have to do first. Because, let's say, because J mu equal to 0, you can just write down from the anti-symmetric property. The d mu symmetry and F mu that. Right? But now, let's say I want to construct in such a field theory where my current is not conserved. Okay. My current is not conserved, then my character of that will be different. So it is not the property of how we play with the meaning, something more than that. Okay, that's why we have to go through each and individual steps.
So, for the fermion case, we consider short representation, we divide the character of the representation.
Okay, let's not think about that. What is the equation of motion? What is the character of the equation of motion?
So for fermion, it is like we said R equals to that's why we will tie R y. So for that case, when we are writing for the free tensor, mu is equal to mu. So there shouldn't have to be character for F which is either 1, 0, 0, 1. So why we get I half time?
It's a vector, right? Vector has alpha and alpha are both the indices. This is not left or right. It's a bicycle.
So that constraint that we had in the from and we had considered the short representation, we are
So that's what I'm saying. What are you doing? Here you are using a fermion. The derivative acting at a fermion is a fermion. Derivative acting at a field tensor. Is it a field tensor? What you are saying, the derivative acting on F mu L giving you F mu R. Is it? No.
so
That's the difference.
the character of the final result we have to substitute.
Character of the what is your constant. This plus I equal to 0. That transform like a fermion. Okay. That's why you are removing the fermion. So that's why let's not make a presumption. What I will do. What in front of me, just do that. D mu acting on the F mu is my current. And current is a vector. And vector in this language is always a bicycle. Okay. That's why I will remove the vector. That's why so basically I am not presuming of the what I have to solve. And I don't know. What I did, I perform this action and then I do a compound motion. And that compound motion tells me what I am producing. It has one alpha node units, one beta units. Now one alpha node is basically one half. And one beta node is basically the half but from the right hand side. Right parallel. That's the half over half. And that is the reason when I am writing a derivative, it has one half over alpha. The derivative also transforms like a half over half. So the action of the derivative on the field tensor offers you something. Look into that, analyze that, and then as far as its characteristic, write down the character. It can be Q4, it can be Q5, it can be Q6, no assumption. What that structure tells you, just follow. Okay? But here also, for example, sometimes we want to improve interaction part. Let's say, for example, if you want to interaction, of course the definition of the smart people should be defined. So the primary lesson from this whole task is basically what is the methodology, rather than exactly what, because these are the basically an example. If you understand the methodology, then you can play with many other. For example, if I know that, for example, let's say you want to construct an operator in high dimension, where you want the equation of motion is taken care in such a way that at the 3-level eco interaction you can have that. You also want your eco interaction to be taken care of. And they should not be related by that in the equation of motion. Then, if you know how to construct smart representation, you will find out the equation of motion, including the eco interaction. Then you find out what is that thing, what are the alpha node indices, and what is this new modified equation of motion's character. And you subtract that, and that will be your smart representation. Okay? This is, I'm asking the free field. That's the result. Okay? Yeah. Any other question?
So for iterative theory also you have to do the same thing or?
Sorry?
For iterative theory.
Yeah. For example, let's say you want to construct a high dimension operator. Okay? And then you say this is my 3-level linear. Now at the dimension C, dimension 10, you want only those operator sets which are not related by the 3-level equation of motion, not the full equation of motion of the 3-level. Because it's your choice how to construct the scenario. But if you understand this method, then what you do, you will not mean blindly this one. What you do, you again write down the character because the long representations are unique. Because it's just a representation, right? And then you find out the equation of motion, including the eco interaction or whatever the kind of interaction you want. Okay? And then you say, okay, what is my character of the equation of motion? You find out that and you subtract that. And that will be your short representation of the manual, which takes care about the equation, not only the free equation of motion, but also the interactive.
But only the equation of motion is not sufficient, like that we see in the
Exactly. For example, now, if I think about the field tensor, now let's say you have a scalar PD and your quantum PD, everything is there. It's one more component structure. Exactly. There are different kinds of symmetries are there, and sometimes, as you know, many of us have worked on something called the softly broken symmetries. Okay, where the current is not exactly constant. Okay, so that means even if it's softly broken, I will not consider the current is constant. So I can track them, which are basically the operators correspond to softly broken. So I can do all kinds of analysis if I understand how step by step get it, not just the final product. So just don't aim for the final product. The final product with certain condition. More important is the journey that you are making. If you understand those steps, then you can create your own theory, and based on that you can create the characters. That is what I am trying to stress. For example, as you know that there is something called we learn that field efficiency. Because the field efficiency also remove the redundancy. And that acts very similarly as if like you are using the equation motion. Right? But the question is it always guaranteed that they are equivalent? The answer is no. If you go beyond dimension 6, let's say you are working dimension 8 operators. The dimension 8 operators there are redundancies. Now if you classify the operators based on the equation motion, you will find out that operator basis is not exactly correct. But there are more redundancies which should be removed by the field efficiency. The field efficiency is more fundamental. That means if I go to the higher dimension actually, okay, and then we don't need to use the equation. So if you are using the equation motion up to dimension 4, it's not sufficient. We have to use the equation motion up to dimension 6 operator. So to remove the complete redundancy of the dimension 8, we have to calculate the equation motion of the dimension 6 or up to dimension 6 operator. And then you can do that. So basically when you do that integrating out, that will be more clear. But the advantage of doing this way is that because the bottom of the approach, we don't need to worry about it. But when you talk about the top down, so when you integrate of some object, you create some effective action. And the effective action when you use in terms of local operator, you get a set of effective operators. And that's a redundant set of operators. Okay. And then you try to remove the redundancy by equation motion, IBP and all those things, such that you can match against this basis. But there we will see that equation motion is a good, classical equation motion is good as long as you are up to dimension 6. Beyond that, it fails. It doesn't give the criteria. How to recover all those things that we learned in the top of that.
For this extra condition that I have the concept current, this I am removing from this long representation.
On the character of the genuine.
But essentially it's adding. Like,
Exactly.
Why is that
No, that is basically what we have removed. It's over removal.
Yeah, so what to remove?
Over removal. That's why it's better to write down the character step by step. So once you have all this constant, and then you go from the bottom. So write down the long equivalence mechanism. Then what you are subtracting, the subtraction, that object's character needs to first compute properly. So we first subtract a genuine with that understanding that this is a conserved current. Once we realize the conserved current, that means basically itself is not short representation. We have constant representation for the genuine. And once we separately constant the genuine character, assuming that this is a conserved, then this genuine character should be removed from here. That's why this is special concept here. Because there, this is psychological. If this is psychological something, then you have to see what is the property of that something. With the understanding that property of that something, if we remove randomly, what will we get? Something wrong. So, if this is not satisfied, then this removal is not equal. This removal is only important when you are dealing with the conserved current. Okay? Why not this part? So now you understand basically the basic difference that we are dealing with, the manual, scalar and the field tensor, how to write down the harmonic character. And here are the short representations, and that will be our working characters for them. Okay? Any other question? Fine. So now, let me go back and summarize how we measure the P part, because there is some confusion some people may have. Let me do that P and then I will do the P first. In between, if you have any question, please ask. Now see how these constants are actually taken care of. Because as you demand that if you write as a polynomial character, then these characters itself are in such a way that the implication by parts is taken care of. And for that we need to know what was the attributive structure of the key. So again, if you recall, I will just go very briefly because it's already discussed last class. So d mu, so we have this chi half x plus 1 by x, so the factor of x, and then you have chi half y and y plus 1 by y, and then if you have the p of q x1, we define and the statistics, and then maybe you can say more symmetric for q I of x. So that's a symmetric product. What is the divide between a normal product and symmetric product? You can see the divide just make a square of this. If I take a normal product in the statistics, if I make a square, what will I get? X square plus 1 by x square plus 2. But if I do a symmetric product, what I get? X square plus 1 by x square plus 1. Why? Because this is, you can think of like an SC2 doublet, two-dimensional representation. So 2 plus 2 is 3 plus 1. The symmetric part is here 3. This is symmetric part 3. And what is the character for three-dimensional representation of SC2? X square plus 1 by x square plus 1. We remove that 1 part. So that's how this is defined. Okay. And once you do that, effectively you are writing statistics of symmetric product of this qxy plus qxy plus qy by x. And then we define these are scalar variables, each are scalar variables. So that's why you know that commutative, scalar variables are commutative in nature. So I can separately write down the infinite series of that. And why I can do this infinite series of this thing? So if you think about each character is basically having a weight omega. Then when you square it, what is the weight of that object? 2 omega square. Then omega cube will have a weight 3. And those are this is the highest weight. And as you know that when you take a tensor product, all the highest weight states are symmetric. Okay. So that's how once we do this thing to the binomial expansion, I skip the expansion which I did last time. So we realize this is basically 1 minus q xy, 1 minus q x by y, 1 minus q y by x, and then 1 minus q y. So now what I do? I have this conformal character when I am writing, along with those short representations, I do this part. Okay? Because now I am in the explicit form, and this explicit form guarantees that basically I have taken care of the symmetric product. This is like when you take a D and all thing, you write down the symmetric product of it. And that will generate and take care of the full conformal character. And that character is sufficient to take care of the equation of motion. So I can guarantee that if I use this character, the equation of motions are taken care of. Okay. But now, as in this discussion, then I can recall you also that why the symmetric product I told you, because just from the conformal point of view, if I have a del mu, if I consider del mu, then you don't need to worry about del because the antisymmetric for which you because del mu counts. So even if you take a product, all the antisymmetric products will zero from there. But because we have translated this in terms of language of EFT, where in a covariant form, where my del mu is updated as d mu, and d mu commutator is not zero, it gives you something called the field tensor. And for us, field tensor itself is primary. So if I include all the combination of d mu, I will basically overcome it. Okay, that's a with the expansion, I generate again all the operators which are symmetric antisymmetric combination of mu. And once I reduce the antisymmetric combination in terms of the mu, I generate the operators in terms of the mu, for example, mu square, mu cube, and so on. But that's not counting because already mu is a primary for me. So I don't want to generate a primary from any other way because primary are my starting point. Okay, and that's the reason here we are focusing on constructing only the symmetry. Okay, that was the fine. So now, what I talk about the derivation of this P inverse and the IB, how that part is important. So IB is taken care of. So now we are interested in this equation of motion. So equation of motion is taken care of IB. Now, before going into this mathematical description of IBP, let's try to understand why this IBP is here. So we are constructing something which will be part of the Lagrangian density. Right? Now, we have this quantity. It's a vertical plus 1 version. Right? That is the action when we are writing. Now, when we are writing these operators inside in the terms of action, so they are basically a space-time integral. Now, if there is some kind of space-time derivatives are acting, okay, then you have a freedom to do the integration by parts. Okay. And because of this structure, we have this one. Integration by parts. Now, what does it tell you? It tells you basically if I have an operator, let's say, fixed. And I have operated in this particular form, they are not independent. Okay? They are related to each other. How? That phi1 mu phi2 goes as minus phi2 mu phi1. And why it goes like this? Because we are working on compact manifold. So total derivatives are basically 0. So then, one way to do is you constant all the operators up to this formula, and then you find out which operators you can relate by the integration by part. But as I told you, for a very complicated theory of having going to high dimension, you have exponentially large number of operators. It's a very difficult task. So what will be our trick? Without performing this IBP, now along with the IBP, the concept of total derivative is always there. Why? Because this you can see, if this is there, then automatically I can construct something, this object, right? That means basically what? So if I have two operators, okay, and I can combine them in such a way that I write down the total derivative term and a new operator, let's say. So what I can say that these two operators or three operators combine together to give me one operator and one total derivative. So I remove the total derivative and it tells automatically that three operators should be written in terms of only one operator. So algebraically if I write down A, or let's say O1 plus O2 plus O3, these are the three operators, and then I write down something O hat plus O4. Okay. So then I remove this quantity to the total derivative and I get the O4. So what I will try to find out that how many ways I can construct in this operator construction the total derivatives, and those total derivatives I will give you. Okay. And now again comparison between the del mu and d mu, in generally we have the total limit term when we say, right? We say del mu because that's why the measure density. But still we use the d mu. Can you answer why? And why does it work? Because the d4x gives you only the space-time part. But still, when you write down inside the Lagrangian, the d mu of something still will drop. But d mu is not only del mu but something more than that. There is a there. But still, that works. Why? The reason is basically at this point, the treatment of d mu del mu is exactly same, unlike the equation motion. Because the equation motion, because d mu doesn't commute, that gives you a mu. That's why we had to introduce not a normal product but a symmetric product, such that we don't do the order of thing. Because we know what we can do with the del mu, we cannot do exactly mimic the same trajectory of calculation with the d mu to return. But here, we don't need to do anything more than that. The reason basically when this derivative is an acting on some operator, these operators are basically singlet. So when the d mu acts on some object, an object has to be singlet object if it's a part of the operator. Right? Invariant. And because if you have a gauge symmetry, it has to be invariant. Because the gauge symmetry doesn't get compensated from the d mu. And if it is so, what does it mean? That means when the d mu acting on the O hat has to be an invariant operator, it's a gauge invariant operator. It doesn't have any gauge. That means that a mu, which is the gauge field, that acts trivially on that operator because it doesn't really act because it's invariant. And that is the reason when you write a totality term, whether you are writing a del mu or d mu, it doesn't matter. Okay? Because many of us use this d mu thing, but possibly we have always this confusion. Okay, so if I split this, I have del mu, I would like a totality term. What about the a mu? The action of the good field, action of the a mu on the invariant operator is equal to 0. So you have to define over group action of the a mu. And that is going to do because this is already an invariant operator. O will have the space-time index, of course, like O mu or something like that, but not a gauge, not it doesn't have a gauge charge. It has to be gauge neutral, otherwise it never have a gauge charge.
So that means in d mu you don't have any gauge.
d mu, we write that in a covariant theory, we write down that d mu in this way. But when you really analyze its action, the a mu or the gauge field inside the d mu act on the invariant operator u0.
So because those are all singlets. So
Exactly.
the singlet representative. So those are those fields in the d mu. So that means
Now as we know,
yeah.
the gauge particle interact with non-singlet object.
Mm-hmm.
And that is why the photon doesn't interact with neutrino. Right?
So yeah, exactly. Mathematically that means you don't have any
Yeah.
gauge. So what? Yeah.
Right? I have seen many students asking this question. That's why I thought let me have this discussion. They always think that okay sir, I just write them this way. And then they knew because literally true, because in principle mathematically d mu cannot be integrated out, only the del mu part. What is the rest of the del mu? You can do that because the del mu operator, the group action of the del mu operator. So you can think of the del mu more expansion. Yet the creation and relation, it acts on the invariant operator is that. That means in our language, a mu acts trivially. So that's why on an invariant operator, the action of the del mu and the d mu are same.
So for example, any complex linear field energy, the kinetic term we can write one total derivative, but then d mu will have phi star phi, which is a gauge symmetry. charge is zero.
Exactly. For example, as I pointed correctly, that if you write down the phi dagger box phi or d mu phi dagger d mu phi, they differ by a term d mu of phi dagger phi. Now, what is this phi dagger phi? It's a singlet. Right? So, similarly, you can think of the, now this same thing, you can go for any arbitrary dimension. So, whether this O is a dimension, 2 dimension, 4 dimension, 6, whatever this thing, dimension is, okay, this will be true. So, we remove those operators which are basically gain unit operator. For the gain unit operator, whether that is a gain or gain unit, it doesn't matter. Because of the gain. It doesn't carry any kind of gain charges. Because that is the purpose. Okay, more fundamental you can think this way. That why? What is the origin of the degree? Because when the phi is transforming, that transformation has some kind of local transformation, right? And that's why when the del mu acts on that, del mu param alpha is the parameter transformation, del mu alpha. And why that even alpha is there, which is transformed, because it is a gain charge. Now let's say, if I ask you phi dagger phi, what is the transform property of phi dagger phi? It doesn't transform. That means having those compensating factor del mu alpha, it doesn't exist here. Right? So that is the reason that covariant derivative and the normal derivative acts exactly similar way. It is just a way of writing. This pops out because we are doing a covariant theory. Right? But what you can do, that once you create a total derivative, you reduce that covariant derivative by normal derivative for a better understanding. Because that is equivalent. Okay. So to tackle this IBP, we have to find out what are the possible ways we can identify those total derivative terms and we can remove them from a construction. That means you construct all the operators and also find out, clubbing them, how many ways you can write the total derivative and remove the total derivatives. It's basically equivalently I am taking care of the integration by parts. And that is the core idea of the integration. It's not like we are not doing mathematical treatment which will do integration by parts manually. No. We are transcending the problem of integration by parts by identification of the total derivative. The both are connected to each other. The total derivative are generated because of the integration by parts. If the integration parts is not there, the notion of total derivative is not there. Okay. That means what? Till this, what we have internal script, we have a special script. We write down the conformal short representations that takes care of the equation of motion. So we generate all kinds of invariant operators. Now once we generate all kinds of invariant operators, what we are trying to do that algebraically, if we write down those operators, and now remember when we are saying that we are doing or clubbing those operators, it has to have the same mass dimension. You cannot write down an integration using the integration by parts. You cannot go from one dimension to one dimension. Right? That is certain difference. We come back to this thing specifically. About the equation of motion and the IBP. In the equation of motion, you generate operators of different mass dimension. For example, let's say because you have derivatives, right? So you reduce operators of different dimensions. But equation IBP actually transcend it suffers the position of the derivative, let me put it this way. And all the allowed subplanes are basically discarded from the total derivative terms. So we classify all the operators, okay, immune to equation of motion, symmetry, and everything. Then let's say I have n number of operators in one particular dimension. I add all the operators algebraically and then find out which of them I can create a total derivative. Once I create a derivative, just remove that. Now, it's not that simple. Because if you remember how we construct the FME, if we do the construction with blindly, sometimes we remove something which is part of that should not be used. So we have to bring construction everything has to be perfect. Okay. Similarly, here the removal business also has to be perfect. In that if you go back to the FMU part, if we just blindly remove only the character of the genuine, we are actually over subtracting something. That means that subtraction should not be done completely if the currents are conserved, and that the Taylor term was the Q4, the scalar part. So what you subtract, if you subtract something more, you have to learn how to add that. That's how you can see that some kind of alternation of the sign. You subtract, which is the minus sign, then you add as a plus sign. And that is exactly what happens in this IBP. If you do one IBP, you will do a minus sign. If you do twice, you will do plus sign. Again, minus, that means it's some kind of alteration of the sign. Then how many IBP you are performing? And why these are there? Because what you are writing as a total negative term, okay, is that quantity conserved, okay, or whether this operator is also a total negative of some other operator. If this operator is a total negative of some other operator, that would be a cascade of construction, and we need to keep a provision for everything. And as you can see, the number of operands of derivatives actually give you the alternation plus minus sign. Okay. And that is what exactly in mathematics language is called the Euler calculation. So, effectively what we are doing, calculating the Euler characters of this variable. And if you have to have a alternate sign, what will do? In this construction P, which is symmetric product of this object, but now we will take a wedge product, or an antisymmetric product of that variables. So the idea would be to follow this Euler character in such a way that whenever we are doing this IBP, okay, so that number of IBP we are performing, that sign has to be taken care of. Everything we cannot assume. If you are removing something, this over removal, you have to compensate that. Again, you remove for the higher form, you judge is it total what you are removing is a complete, or you are over removing something, you add that. And you have to get a cascade of doing that. And that's how the Euler character is generated. So let's see how it happens. Any question? Because I told you that it's a concept, right? So I can write if you change the gain you have current. Okay? If it is so, then only. Or I'm repeating that operator is getting there. And then, as I told you, that EOM is example, which is I have EOM 5 plus EOM 5 I got 5. You can represent right now. Right? So this is what we are. So now, let's say, what is this genuine? This genuine is basically genuine. Okay? The third bracket tells you that they are antisymmetric uses. Okay? So these are basically three tensors, antisymmetric in unit. Okay? So now, if I add genuine and genuine, what did I do? Half of the commutator. Okay. And I have and then this is something But now, coming back to this discussion, that we are interested in the total derivative of only those objects which are derivable. Let's see what happens, because at this point the current will not be derivable. If it's so, then it's fine. It's not in derivable. Then we can see that even the total derivatives are not zero. The current is not constant. Tell me, the derivative. But what happens if I start with a derivation operator? So for derivation operator, let me call it. So any number of derivative acts on that basically will be zero. It's not like whether it's a dmu or dnu. You might think of, okay, so I'm constructing a dmu anticommutator in f nu, but the f nu act on that point invariant operator will be zero. Right? So that's why it's not about the dmu acting on the invariant operator zero. Any number of dmu acting on that invariant operator is zero. That's all I can guarantee. But there's something more than that. So, if this is an invariant operator, okay, so what's the character for that? One, invariant is scalar. Remove the boxes, right? This character is basically 1. So now, if I have to remove this del mu j mu, okay? See any scalar form you can write down? That means the derivative of that operator, divergence of that operator, I have to remove. Okay? So I remove this one. I start the scalar operator, then the total range of the scalar operator is basically 0. So I remove that quantity. And total range of the scalar operator is transformed like a vector. So I remove that. But then I have j mu equal to del mu, let's say b mu, and then del mu j mu equal to 0. That tells you del mu, b, mu equal to 0. So this is a further constant on that thing. That means what I remove completely, but there is an additional constant that. Remember the f nu character the way you put that thing. So I have to add it back this time. This is the wedge product. So then, what else subtract again? The odd number. I get third derivative acting on that same operator. If that operator is still not 0, I remove that part. So I remove basically q by done by q. But what I find out, again, by the arithmetic property, I have to add back the q4 part. So I add the q4 part. And then I continue doing this thing until basically this equal to 0. So depending on the characteristic of the operator and its property, I I have a defined length of this kind of chain. But what I can do in turn, I can write down a very infinite series of that. Because if I have an infinite series, so whenever it's required, so I can do that. Right? Now, let me give you one example that is possibly easy for you guys. So let's say I take my f of x as my d1. Okay. And then I can calculate j1 as my j2 b21 equal to minus j2f and j2 as j1 b12 equal to j1f. So I choose my function f of x equal to b1. And then I calculate j1 is the derivative of that, the derivative acting on that, taking my plus derivative, and then it's acting on j2 because b2 is 1. Then if what I get is the L1, J1 plus L2, J2 equal to 0. Right? Because it's a minus and plus sign and L1 there to common, so basically I get 0. So I start with B12, I remove this part, which is basically in my language, I remove this part, but they satisfy again additional constant this thing. So I have to add it back, and which is this one. Now as you can see, if it has more indices, let's say it has 4 or 5 indices, then you have to repeat doing this thing. That's what I'm saying. And why I am taking this function? Because my intention is to not to stop any particular dimension. If I want to in let's say 10 dimension operator set, then you can see you can make mu to the power 5. Right? 3 to the power 5. So that explicit, I mean 10 such indices are there. Okay, that means for that I have to do multiple IBPs again and again. Okay, so I am keeping that function by creating this infinite series. Whenever up to any RP dimension, whenever I require, I have the function calculated. If I only look for that dimension 6, I possibly do not need this series at all. I just have to do the final one. But having an infinite series automatically takes care of all the total derivatives, and while constantly the total derivative, whether there is some additional removal if it is being done, okay, then and suitably added. And that's why this creates an alternate series, and which is very unique in the wire characters. Okay. So yeah, let me give you one more example that will be helpful. Now, let's say I have mu, which is basically my L0, 0, mu. So C belongs to what? Okay. So now, what I can calculate is the following: L mu, D mu, L mu, L rho, C, rho mu, equal to 0. So this is my minus C cube. But then again, if this mu rho is divergence of other higher form object, sigma mu rho, then I add this. So what I am subtracting, is it a total divergence of some other object? Whether that object is also related to some other object, whether that object is also related to another object, that is the cascade we have to follow. That you can see, I start with B mu, but B mu is a total derivative of 3 form object. These 3 form is a total derivative of some 4 form. These 4 objects, the probability of 5 and so on. So that means basically whether I am talking about an nth form, whether it is a probability of n plus 1 form or not. That is the classical form. And now you can see, if you go from n plus 1 form to 1 form object, you have n number of derivatives, and this n will be alternately even and odd, and that is how connected with the plus minus multiplications. And this plus minus thing, we can always add the way you have, because that's the arithmetic. And now, if we do hold this sum, and that sum is actually your P inverse. And that is what we call 1 by P or P inverse. Okay. And that is written in this particular form, P inverse uxy as sum of a to infinity minus e equal to k. Right? So then one can show literally that what we have this P times this P inverse equal to actually identity. So those are the symmetric product of that. This is a Wedge product of that, and if you glue them, you get an identity or another. So then what is the role of the P inverse when you write down this thing? So now when you write down the hardware, we have 1 by P sitting here, okay? And then when you write down the prefix of this conformal group character, next is the arithmetic, like this, okay? 1 by P in the hardware. And these actually have a short representations, which are the Q chi J1, Q chi J2. This P is sitting here in the prefix, and this P inverse is basically as an over factor in the outside. So that means through the prefix, all the event operator, including the equation of motion, constant you generate. And then at the end of the day, these guys will filter all the operators by removing the probability terms, giving the whole set of operators which are basically not suffering from IBP and equation. And that is why the presence of P and P inverse are separate. Because equation also has to satisfy the order, and that's why it goes in the character. But P inverse is basically filtering the whole set of invariant operators. That's why 1 by P is sitting outside, it doesn't go in the character. And now we can see we are almost ready to write down what Hilbert series. So next class, I will write down the Hilbert series for the standard model. Because it's more complicated experimentally proven theory to write down the Hilbert series. Right? So you will see how the field tensor, how the scalar field, how the Feynman field transform, how to write down the character for individual fields which contain different kind of gauge quantum number, and how the space-time animals that space-time handles. This won't go here. Right? But intensity handle doesn't have any one value. It is just a overall factor. Okay. And to do this part, so the full Hilbert series will be done, and you get exactly in the two-pivot polymer paper, you put it like this, and you get the result for the unit. The second assignment will be basically, I am given 2, 3 toy models where I give you the symmetry and the quantum field, how their quantum numbers. Okay. You have to construct invariant operators, dimension 6, dimension 7. Okay. But it is that simple. What I ask you guys, give me all the operators without filtering in the equation of motion and identity. Okay. That will let's say some 10 operators. Then I said, okay, use only equation motion, but not IBP as a constant. It will be some number of orders, 6. And third will be, now invoke IBP, but not use equation motion. So that's what you get an idea how individual constants are playing the role. And finally, once you have all the constants, what is the composite of order? That will clear up the whole game of order constants. Okay, so that will be your second assignment, which I will hand over. After that, we are going next day. Okay, next page, when they by any chance holiday? What holiday? What kind of holiday is this? Religious holiday, then I will see.
No. Yeah, some E.
Okay, so then
Onam
goes.
is
Okay, so then we'll skip the Wednesday and this thing. Possibly then actually I can create the assignment as send you. Good if you have the class. Yeah, what you can do. I am always ready to take the extra class on Wednesday. I can book the theory, do everything. But only we cannot call a class, we have to call a discussion. And if you guys are ready for that, then I am. So let me know. Do you like the this just need one more class to wrap this thing. We are almost ready to write that also. I mean, I guess this is half an hour like that. When we just not the full class. I can take the afternoon also if you guys are fine with that. Is that okay? We'll take a discussion of half an hour. Not a class. Okay, so just half an hour. Okay. Around, so I drop an email, then we will have a discussion. I want to understand what is going on. Okay. So around 3 or so, is that okay? Or so 3, I will 3 so we can have the discussion here. So after that, you can use the time for the assignment. Right? Then I will go the deep tunnel method and all those things. Okay. But I hope you get the idea of what is going on. Please go through, and if you have any